Welcome to this, the fourth lecture in our series on fundamentals of transport processes. In the first lecture, I tried to give you a motivation about why we need to study transport processes, because transport is essential for all the physical or the chemical transformations that take place. And the next two lectures, we looked at dimensional analysis, what that can do for us, in terms of defining how to get a flux based upon the concentration difference, how to get a heat flux based upon the temperature difference, and I also told you about momentum fluxes and differences in velocities. And last class we specifically did a calculation for specific processes. For example, first we looked at the flow in a heat exchanger, where it is of interest to calculate what is the transfer rate of heat from the inside to the outside as a function of the temperature difference, the speed with which the fluid is moving, as well as the fluid thermal and mechanical properties. And we got a relationship between four dimensionless groups. One was a non-dimensional flux for heat, then there was a Reynolds number, which was the ratio of inertia and viscosity, another dimensionless number involving the specific heat, the conductivity and the viscosity, and an aspect ratio, which was basically the ratio of length to diameter. And I said you can reduce it to this form, but not further. If you want to go further, you have to do experimentation, change the Reynolds number, change the Prandtl number, and see how the Nusselt number changes or the average heat flux changes. And you get different correlations depending upon whether the flow is laminar or the flow is turbulent under different conditions. And you can actually have diagrams which actually plot the left hand side versus the right hand side. And then we looked at the heat transfer and mass transfer from the surface of a catalyst particle. And there I told you the fundamental numbers, the non-dimensional mass flux, a Sherwood number, a ratio of a mechanical quantity, viscosity, and a mass transport quantity, the diffusion coefficient, and the Reynolds number, basically because the fluid flow is what is transporting mass to the surface. And we looked at two different correlations, for laminar flow and for high and low Schmidt numbers. And I briefly mentioned that for the mass transport problem, nothing changes in these correlations. The numbers are all exactly the same, except you substitute the Nusselt number for the Sherwood number and the Prandtl number for the Schmidt number. And those same correlations will work for mass heat transfer as well. So, there is a fundamental analogy between mass, heat and momentum transfer. And we looked at the physical interpretation of how that the equivalence comes out. From the physical interpretation of diffusion, this is a general diffusion equation. This equation is a general diffusion equation for any quantity. It can be mass, it can be heat, it can be momentum. Flux of quantity, this is important, so we will go through it once again. I have a slab of fluid of some length L and cross sectional area S. S is the area, and I apply a concentration difference across the slab of fluid of length L. The flux, the amount that goes through per unit time, is going to be directly proportional to the surface area S, because if you make the slab wider, there is going to be more mass going through. The amount is going to be directly proportional to the difference in the concentrations, because if I make the two concentrations difference higher, I am going to have more material going through. The amount of material is also going to be inversely proportional to the length L, because as I make it larger and larger, there is going to be less amount that is going through. Rather than write an equation for the amount of material going through, I can write an equation for the flux, amount per unit surface area per unit time. So, since the amount of material going through is proportional to the surface area, the flux, which is the amount per unit area per unit time, is independent of the area. It only is proportional to the difference in concentration. It will increase, of course, if you make the concentration difference larger. It is inversely proportional to the total length. As you make the slab thicker and thicker, the amount of material going through is going to become less and less. This is Fick's law. of diffusion. And this coefficient here, the diffusion coefficient, d is the diffusion coefficient. Heat conduction. I take a slab of material. This heat conduction argument actually works for both fluids as well as solids. Okay. Solids also follow the same conduction equation as fluids do. Okay. So, heat conduction equation, the heat flux across a material. I have a material with area S, okay, and I apply a temperature difference across the material. The thickness of that material is L. So, the heat flux is the heat going, so the heat going through is proportional to the surface area of the material, proportional to the difference in temperature, inversely proportional to the length of the slab of that material. Okay. So, the heat flux, which is the heat per unit area, is going to be independent of area. Okay. It's because you have already taken the heat transferred per unit area per unit time. It is proportional to the difference in temperature. Okay. As you make the temperature difference larger, more heat is going from the region of high temperature to the region of low temperature, and it is inversely proportional to the length of material. Okay. So, it is k delta T by L, and this is Fourier's law for heat conduction. For heat conduction. Okay. Now, in my diffusion equation, I said that the flux of a quantity per unit area per unit time is equal to a diffusion coefficient times the change in density of that same quantity. Density of that quantity, quantity per unit volume, the change in that density of that quantity per unit length. Okay. So, in this case, the density is the energy density. Okay. So, I have got k times delta T by L, but I have to express it in terms of the change in the density of that quantity, which is energy itself, and energy has to be written as rho Cp times T. Okay. So, the change in the rho Cp times T divided by L. Okay. And obviously, if I write it in this form, the coefficient that appears in front is k divided by rho Cp. Okay. So, I get this thermal diffusion coefficient alpha, okay, times the change in that quantity per unit length. So, alpha is the thermal diffusivity. Okay, thermal diffusivity. Okay. And this diffusion coefficient as well contains the dimensions of length square per unit time. Okay. For momentum, the shear stress acting at a surface, I take a slab of fluid of length L and apply a velocity difference across that. Okay. Within the slab itself, I have a linear variation of velocity with position. Okay. The shear stress, which is the force per unit area. Okay. Force is rate of change of momentum. Okay. So, it is the change in momentum per unit area per unit time. So, it is a flux of momentum, okay, is equal to some coefficient times the change in density of that same quantity. That quantity is momentum. So, I have to have a change in density of momentum per unit length. Momentum is mass times the velocity. That means that the momentum density is the mass density times velocity. So, change in momentum density rho times u divided by L, and the coefficient that appears in front is mu by rho, which is the kinematic viscosity. Okay. So, therefore, these are the three diffusivities for mass, momentum and energy. For mass, the diffusion coefficient is the usual diffusion coefficient in Fick's law. For energy, the diffusion coefficient is k by rho Cp. Alpha, the thermal diffusivity, where k is the conductivity and rho and Cp are the specific heat and the density respectively. For momentum transfer, the diffusivity is the viscosity divided by the density and is referred to as the kinematic viscosity. Okay. And you can easily verify that both of these have dimensions of length square T inverse. Okay. For example, the viscosity is mass length inverse T inverse, the density is mass L power minus 3. Okay. So, if I take the ratio of these two, I will get L square T inverse, okay, as the ratio of the viscosity and the density, and therefore, all diffusion coefficients will have dimensions of length square T inverse. This gave us a physical interpretation for what all those dimensionless numbers mean. Okay. The mass diffusivity D has dimensions of length square T inverse, thermal diffusivity alpha k k by rho Cp has dimensions of length square T inverse, and momentum diffusivity nu has dimensions of length square times T inverse. Okay. Now, let us look at what is the rate of convective transport. Convective transport is the transport due to the convection of material. Okay. So, if I have some slab of material of surface area S, okay, and it has some velocity field here, it is moving with some velocity u, okay, then material is transported because there is a velocity for this material, okay, because the material has a velocity, is going to get transported even though there is no difference in concentration across two different positions. Even when there is no concentration difference, there is still going to be material transported because of mean convection. Okay. So, for example, in the reactor problem, there was convection that was bringing in mass at the inlet and convection taking the product out at the outlet. In the case of the heat transfer problem, heat was coming in at the inlet due to convection. Okay. So, convection is transport even when there is no change in the concentration or the temperature or the momentum. Okay. What is the amount of material that is transported? Okay. So, let us look at two times, at time t and time t plus delta t. Okay. So, at time t there is a certain amount of material that has not yet entered. At time t plus delta t, the material, some of the material that was here has come down into this differential volume. Okay. The distance it has moved is equal to u times delta t. Okay. The distance it has moved is equal to u times delta t, okay, within a time delta t. Okay. So, that means that the amount of material that has come in is equal to this volume that has come in times the concentration of that volume. Okay. The volume that has come in is equal to the surface area times this distance u delta t. The volume that has come in is surface area times u times delta t. Okay. So, the mass that has come in is going to be equal to the volume times the concentration. Okay. Volume times concentration, which is equal to C into S into U into delta t. Okay. So, this is the volume that has come in, okay, S into U into delta t, and the mass in is C into S into U into delta t. Okay. Therefore, the total mass in per time, okay, mass in per unit time is equal to C into U into S, okay, divide by time, and the flux is equal to mass in per unit area per time is equal to this mass in per time divided by the surface area S, which is just going to be equal to C into U. Okay. So, the flux is just equal to the concentration times the velocity, flux of mass. Flux of energy is equal to the energy density, the energy per unit volume into velocity. Flux of momentum is the momentum density, that is the density, the momentum per unit volume into velocity. Okay. So, therefore, the convective transport, okay, the flux will be equal to just the concentration of let me just write, it's equal to density of quantity into velocity. Okay. Now, the flux due to diffusion, okay, so the flux due to diffusion, okay, so the flux due to diffusion is equal to diffusion coefficient into the change in density divided by length L. Okay. The flux of quantity is equal to diffusion coefficient times change in quantity divided by the length L. That is the flux due to diffusion. The flux due to convection is just equal to the concentration times the velocity. Okay. Therefore, the ratio of those two, okay, will give you the ratio of those two will give you a ratio of flux due to diffusion and flux due to convection. Okay. So, in this case the Reynolds number is the ratio of the flux due to convection u times length, okay, divided by the kinematic viscosity. Okay. The Schmidt number that we had seen earlier was the ratio of momentum diffusion and mass diffusion. Momentum diffusion coefficient, kinematic viscosity has dimensions of length square time inverse. Mass diffusion coefficient has dimensions of length square time inverse. Okay. The Prandtl number, we saw that that is equal to the ratio of momentum diffusion and thermal diffusion, both of which have dimensions of length square T inverse. The Reynolds number was the ratio of convection and diffusion. The kinematic viscosity has dimensions of length square T inverse. Velocity is length per unit time. So, if you take u into d by kinematic viscosity, I get a dimensionless number, ratio of convection by momentum diffusion. One can also write the ratios of convection by mass diffusion and convection by thermal diffusion. Okay. So, these dimensionless numbers, the Reynolds number, the Prandtl number and the Schmidt number, give you either the ratios of two different diffusivities or the ratios of convection and diffusion. Okay. So, this will be a recurring theme in the course, the ratio of convection and diffusion or the ratio of two different diffusivities. Okay. Of course, there are other dimensionless numbers that are also important, okay, for our course. Okay. We have seen already some of those. Okay. One could, for example, have dimensionless numbers involving surface tension. Okay. So, the dimensionless numbers that involve surface tension are called the capillary number and the Weber number. The capillary number is written as mu u by gamma, where gamma is the surface tension, mu is the viscosity and u is the characteristic velocity. Okay. So, this is the ratio of viscosity divided by surface tension. Okay. And one can also have a ratio of inertia and surface tension, and that is what is called as the Weber number. Okay. This is written as rho u square d by gamma, which is the ratio of inertia by surface tension. Okay. You could have dimensionless groups involving gravity. Okay. So, for example, we already seen one, which is the Freud number, which was u d by g, okay, where d is the characteristic length. Okay. I am sorry, this should go as u square by g d, okay, Freud number. Okay. And you can also have something called the bond number, which is rho g L square by gamma, which is the ratio of gravity by surface tension. Okay, the Freud number is the ratio of inertia with respect to gravity. Okay. So, these are important dimensionless numbers, for example, which involve surface tension, gravity and so on. There are other problems where it is not very clear what ratio they exactly represent. Okay. One such important case is actually what is called natural convection. and I will take a little bit of time to explain what exactly this is, okay, because it is important, especially in heat transfer problem, because as you probably know, there are two main mechanisms of heat transfer. One is forced convection and the other is natural convection. Forced convection heat transfer is where the transfer of heat, the velocity field is basically determined by the external action, by the pumping, for example, okay, of a fluid through a tube or around an object, and that velocity field is what convects the heat away from that object. Natural convection is the other way. The surface is heated, and because of the fluid is hot near the surface, the density is lower, and because the density is lower, it tends to rise because of buoyancy effects. Okay. So, the velocity field itself is created by the heating of the surface itself, okay, and so in that sense natural convection is a little more complicated. Okay. So, let us say that you had a buoyancy force, okay, if the force acting on the surface so for example, if you had some heated object, you would have fluid rising upwards, okay. If this was the hot temperature and this is cold, you would have fluid rising upwards because near the surface the fluid is heated and the density of that fluid is lower, okay, and because of that it rises upwards. Okay. If you look at any parcel of fluid here, okay, there is an upward force due to buoyancy that acts on this parcel. Okay. What is the force due to buoyancy? That force, okay, is equal to the change in density, the difference in density between this and the outside, and the gravitational acceleration. Okay. So, this is a force per unit volume acting on a parcel of fluid because its temperature is higher than the temperature outside. Okay. What is delta rho? Okay, the temperature of that parcel of fluid. This is equal to the density times the coefficient of expansion times delta T, okay, where beta is equal to the change in density due to unit change in temperature. Okay, beta is the coefficient of thermal expansion. So, the force is equal to rho beta delta T times the gravitational acceleration. Okay. This force causes a velocity in the fluid, and what is that velocity going to be? Okay. One can consider two different cases. One is where the force exerted due to this is balanced by the inertial stresses in the fluid. The second is where it is balanced by the viscous stresses in the fluid. Okay. It will not make very much difference from the point of view of dimensional analysis which one you consider. Okay. But let us for the moment consider that this force is balanced by the viscous stresses in the fluid. Okay. If this object has a diameter d, okay, and if this force is balanced by the viscous stresses in the fluid, okay, then the characteristic velocity with which the fluid is moving upwards, uc, okay, just from dimensional analysis will go as f times d square by mu, okay, where f is the force per unit volume. Okay. You can very easily verify that this ratio has dimensions of velocity itself. So, that is the characteristic velocity with which the fluid is rising. Okay. With this characteristic velocity, I can now write down a Reynolds number, okay, because the Reynolds number is the ratio of inertia and viscosity. Okay. And if I write down the Reynolds number with that characteristic velocity, goes by the name of the Grashof number. This is equal to rho uc t by mu. Okay. And I substitute for uc here, so I will get rho t by mu into uc was f d square by mu, okay, which is rho d by mu into t square by mu into rho beta delta t times g. Okay. So, you assemble all terms together and you will get rho square t cubed beta g delta t by mu square. Okay. So, this is the Grashof number. Okay. It is a complicated number. Okay. It looks like it has many different factors in it, but if you break it down to its basics, it is basically the ratio of inertia and diffusivity, where in inertia you include the characteristic velocity, which is obtained by a balance between the applied force, which is the force due to the difference in density, and the viscous stresses. Okay. So, this is the Grashof number, and one can also get a different number called the Rayleigh number. Okay. In the Rayleigh number, you are not balancing taking the ratio of inertia and viscosity, but rather you are taking the ratio of convection and thermal diffusion. Okay. So, the Rayleigh number is basically equal to U c times d by the thermal diffusion coefficient alpha. Okay. And this is equal to U c times d by the thermal diffusion coefficient is k by rho C p. Okay. So, this is equal to rho C p d by k into U c, which was t square by mu into rho beta delta t times g. Okay. So, this works out to rho square C p d cubed beta delta t g by mu times k. Okay. Once again a complicated number, but if you break it down to the ratio of different forces, it is quite easy. It is basically a ratio of convection and thermal diffusion. Okay. Where in convection I have taken the velocity that is caused due to the difference in density and scaled that by the and used the balance between the force that is caused due to the difference in density and the viscous forces in the fluid. Okay. So, the fundamental numbers for convection are the Grashof number and the Rayleigh number. Okay. So, if I had heat transfer, a natural convection heat transfer, instead of having the Reynolds number, okay, the Reynolds number is ratio of inertia and viscosity, where the velocity that you take is the applied velocity in forced convection. In natural convection, you have to take the velocity that is obtained due to the density difference, due to the buoyancy effects. So, the Nusselt number in that case will be a function of the Grashof number and the Prandtl number. Okay. And then we have non-dimensional fluxes. Okay. Yeah. Okay. We have already seen those. Okay. The Nusselt number and the Sherwood number. Okay. So, for heat and mass transfer problems, the Nusselt number and the Sherwood number will be written in terms of the ratio of all other forces. The Reynolds number, the Prandtl number or the Schmidt number as the case may be, and surface tension forces if they are important, gravitational forces if they are important. We will know if surface tension is important if the Weber number or the capillary number is large, is small, then surface tension is important, and similarly gravity will be important if the Froude number is small. Okay. So, that is the reason that in the dimensional analysis that we did earlier, we always got these numbers coming out, okay, because these numbers are dimensionless fluxes and they are written in terms of the ratios of convection and diffusion of different kinds. Okay. So, for example, you can broadly classify the correlations as flow through pipes and channels. Okay. We already saw those for the flow through a pipe in the heat exchanger problem. Okay. The Nusselt number for laminar, Nusselt number is equal to 1.86 Re power 1/3 PR per 1/3 d by L per 1/3 mu by mu W per 0.14. Okay. Two things here. First thing is I can write this whole thing 1.86 Reynolds number times the Prandtl number is the Peclet number P power 1/3. Per 0.14. Okay. So, the Nusselt number is depending only upon the ratio of convection and diffusion of mass. Okay. The ratio of convection and diffusion of momentum is not appearing in this correlation. Okay. apart from this correction factor that is there. Okay. If instead of a heat exchanger problem, I had the equivalent mass transfer problem, that is, there was solute flowing through the tube and it was diffusing across the surface through a porous surface to the fluid outside. Okay. I would get exactly the same correlation, okay, for the laminar flow. That is, the Sherwood number is equal to 1.86 Re power 1/3, Schmidt number power 1/3, d by L power 1/3. In this case, we assume that the diffusion coefficient does not change across the cross section of the tube. Okay. And the reason is because these transport problems, they are determined by two effects. One is diffusion and the other is convection. In one case is diffusion of mass, in the other case is diffusion of heat, but both of those follow the same relations, okay, for the flux as a function of the difference in concentration or the difference in energy density. Okay. For a turbulent flow, the Nusselt number is equal to 0.023, right, into Re power 0.8 PR power 1/3. Okay. In this case, I cannot reduce it to the Peckley number alone, okay, because the powers on Re and PR are not the same. So there is a dependence both on mass diffusion and momentum diffusion in this case. Okay. So this is the seated rate. Okay. And if I were doing the equivalent heat mass transfer problem, I get exactly the same. So that was for flows through pipes and channels. Okay. In this case, these correlations are for flow through cylindrical pipes. For flow through other kinds of geometries, these coefficients here will change, okay, but the general relationship will not change. Okay. For other kinds of geometries, these powers will remain the same. Okay. So the powers that I have here will end up remaining the same. We will look in this course at why these powers come about. Okay. The other broad class of problems is flow around objects. And in this case, this is the object, and this has, let us say, a temperature T1 and T2 far away, and there is a flow around this object. Okay. And you want to know what is the average flux either going into this object or coming out of this object as a function of the temperature difference and the velocity. We usually use the velocity far away from the object, because obviously the velocity is going to change as it comes near and flows around the object. Okay. The equivalent heat transfer problem mass transfer problem C1, C2, and there is a flow around this object. Okay. And in this case, the non-dimensional fluxes are based upon the diameter of this object. Okay. And for example, for laminar flow and low, okay, Rayleigh number, okay, I will have a correlation of the form Nusselt number is equal to 2 plus 0.6, okay, Re power half PR power 1/3. So in the limit of low Peckley number, that is, the Peckley number is Reynolds number times Prandtl number. So if both of them are low, that means that diffusion is dominant. Peckley number ratio of convection and diffusion. So if it's small, that means that diffusion is dominant. This Nusselt number is going to a constant. Okay. And that is because diffusion is large, there is no convective effect, okay, and therefore if I remove the velocity from my dimensional analysis, I can get only one dimensionless group, that is QD by K delta T. Okay. If velocity is no longer a factor, this is the only dimensionless group that is left. Therefore, it has to go to a constant value. Okay. Similar for mass transfer, the equivalent is 2.0 plus 0.6 Re power half Schmidt number power 1/3. Okay. So, these are the correlations for low Peclet number, okay, for laminar flow. Okay. In the limit of high Peclet number, convection is becoming important. Okay. In the limit of high Peclet number, convection is dominant, okay, and because of that I will have different forms of correlations. Okay. I will have Nusselt number is equal to (1.24) Re power 1/3 PR power 1/3. Okay. And you can see that this is equal to 1.24 times Peclet number power 1/3. Okay. So, this is still in laminar flow. Okay. So, Nusselt number goes as the Peclet number to the limit of to the power of 1/3. Peclet number ratio of convection and diffusion. So, effect of convection is large, but still the Nusselt number is depending upon the diffusivity, is depending upon the Peclet number. Okay. And the equivalent for mass transfer is Sherwood number is equal to 1.24 times Re power 1/3 Schmidt number power 1/3. Okay. So, these are the kinds of correlations that are available. Okay. And we will see during this course why these kinds of powers come up. Okay. Why do we get these kinds of powers for mass and heat transfer? As I already told you, the diffusion mechanisms are the same, so the correlations end up being the same. Okay. The other kinds of correlations are for natural convection. And in this case, the natural convection, it depends upon the kind of configuration you have. If you have a sphere heated in a fluid, you will get one kind of correlation. If you have a cylinder, a long cylinder heated in a fluid, you will get another type of correlation. If you just had a heated flat plate, you will get another type of correlation, but they all follow some basic relationships. Okay. So, for example, if you have a sphere in a large body of fluid, okay, around which there is natural convection going on, I will get Nusselt number is equal to 2 plus 0.59 Grashof number times Prandtl number per 1/4. Okay. Okay. This is for very low GR times PR. Okay. Less than about 10 power 4 or so. Okay. For Grashof times PR between 10 power 4 and 10 power 9, I will get relationships of the form Nusselt number is equal to 0.518 GR times PR power 1/4. Okay. This is for the limit of PR small compared to 1. Okay. In the limit of PR large compared to 1, I will get the Nusselt number is proportional to PR per half times GR per 1/4. Okay. And once again you can see all these powers that are coming up, okay, half, 1/4, okay, 1/4 here and so on. Okay. We will try to derive why these relations are of this form, okay, in the remainder of this course. So far I have talked about non-dimensional fluxes for mass and heat. What about non-dimensional fluxes for momentum? Okay. Historically, the non-dimensional fluxes for momentum have been defined differently. Okay. For the flow around an object, okay, the non-dimensional flux is defined as the drag coefficient. Okay. Drag coefficient is the drag force by the area of projection. Okay. So, if I have a sphere and there is a velocity that is going around the sphere with free stream velocity is u, sphere diameter is d. Okay. The projected area is the area perpendicular to the velocity vector. Okay. So, in this case the projected area is equal to pi times r square, where r is the diameter of the sphere, radius of the sphere. So, it is pi d square by 4. Okay. So, this is the measure of the stress, the force divided by projected area is a measure of the stress, and this is divided by half rho u square. Okay. So, that is how the drag coefficient is defined. Okay. If you recall, we solved the problem of the flow past of the settling of the sphere settling in a fluid, okay, with diameter r. Okay. The drag force was equal to 6 pi mu r u. Okay. In that problem, as I said, at low Reynolds number, Stokes drag law. Okay, which is equal to 3 pi mu times the diameter times the velocity. Okay. So, therefore, F t by A p will be equal to 3 pi mu d u by pi t square by 4, okay, which will be equal to 12 mu u by t. Okay. That is the stress, force per unit area. Okay. So, C d is equal to 12 mu u by d into half rho u square, okay, which is equal to 24 by rho u d by mu. It's equal to 24 by r e. Okay. So, you must have studied the correlation for the drag coefficient, okay, for the force on a sphere settling in a fluid. Okay. In the limit of low Reynolds number, where the forces are primarily viscous, the drag coefficient is given by 24 by r e. Okay. So, if I plot log C d versus log r e, I get something that goes like this. Okay. But at some point, as the Reynolds number increases, there is a transition from the flow around the sphere to a more complicated velocity profile, where I have the separation of the boundary layer and the formation of wakes at the back. Okay. And once that happens, this drag coefficient goes to some other constant value. Okay. It goes towards 2. Okay. And we will come back and see why that is the case. Okay. You can see that if the force were due to the inertial force of the fluid, then the force acting is just going to be equal to half rho u square acting on the surface. Okay. So, the drag coefficient has to go to a constant value. Okay. So, this relationship, this C d, the drag coefficient, is a scaled momentum flux. F t by A p is an average momentum, average force per unit area acting on the surface perpendicular to the direction of the flow. Okay. So, F t by A p is an average stress or a pressure acting on the surface. As I said, stress is nothing but a flux of momentum. That scaled by half rho u square. Okay. Flux of momentum is force per unit area. Okay. Half rho u square. Half m u square is kinetic energy. Okay. So, half rho u square is kinetic energy per unit volume. Okay. So, I am scaling the force per unit area with the energy per unit volume, and they have the same dimensions because energy is force times length. Okay. So, force per unit area, the stress, average stress is being scaled by the energy per unit volume, and that is how you get the drag coefficient. I could very well have scaled this with the viscous scales. Okay. In mass and heat transfer, the non-dimensional stresses are defined with respect to viscous scales. Okay. So, with respect to the diffusion coefficients. Okay. So, in this case, the mass flux, non-dimensional mass flux, is defined with respect to a diffusion coefficient. Heat flux, the non-dimensional flux, is defined with respect to the diffusivity of heat. Okay. And that is traditional. Okay. It's since diffusion is the mechanism, obvious mechanism of transport, it is traditional to do that. Okay. Whereas, in the case of momentum flux alone, historically the flux has always been scaled by convective scale. Okay. I could have scaled it with respect to the viscosity. I could have used the viscosity for non-dimensionalizing it, in which case I would have got a diffusion scale. Okay. I would have scaled the stress by a diffusion scale. Traditionally, it is done by a convection scale, and that is the reason that C d is effectively a non-dimensional momentum flux. Okay. And it goes as 1 over Reynolds number in the limit of very low Reynolds number. Okay. When it goes as 1 over Reynolds number, the force is due to viscosity alone. Okay. And then at some point there is a transition. Okay. So, this was for flow around an object. The non-dimensional momentum flux for the flow around an object is the drag coefficient, with the difference that the drag coefficient is traditionally scaled by the inertial scales, the kinetic energy per unit volume, and not the diffusion scales, which would have been the kinematic viscosity times the velocity. Okay. How about for the flow through tubes? For the flow through tubes, okay, the non-dimensional momentum flux is defined with respect to the shear stress acting on the wall of the tube. Okay. Okay. So, the wall stress tau w is the shear stress acting on the wall of the tube. Okay. It is the force per unit area acting on the wall of the tube. Okay. And the non-dimensional flux is defined as the friction factor, okay, which is equal to tau w by half rho u square. Tau w is the viscous stress, the force per unit area acting on the wall of the tube, force per unit area. Half rho u square is the kinetic energy density, the energy per unit volume, and both have the same dimensions. Okay. So, this F is called the friction factor. Okay. You can also write it in terms of the pressure gradient, okay, because whatever force is exerted on the walls of the tube, okay, due to the fluid flow, okay, so the walls exert a force backward as the fluid is flowing forward, the walls are exerting a backward force that has to be balanced by the difference in pressure between the two ends. Okay, so, you apply a pressure gradient across the two ends of the tube to balance the force that is exerted due to the stress backwards. Okay. Force exerted due to the stress is equal to stress times the cylindrical area. Okay, so, this is equal to tau w, okay, into 2 pi r times L. Okay. This has got to be equal to the pressure times the cross sectional area, okay, that is equal to the difference in pressure times pi r square. Okay. Therefore, delta P by L is equal to tau w by R. Okay. Okay. And from that I will get the friction factor is equal to delta P by L d by 2 rho u square. Okay. So, this is equal to 2 tau w r, which is equal to 4 tau w by t. Okay. Okay. So, this is the friction factor expressed in terms of the pressure gradient. Okay. Now, what would you expect to happen? Okay. There are two limits. One is the limit of very low inertia, and the other is the limit of very low viscosity. Okay. The ratio of inertia and viscosity is the Reynolds number. Re is equal to rho u d by mu. Okay. When this Re is less than 2100, the flow is in the laminar regime. Okay, that means there is a balance between the viscous stresses in the fluid, okay, and the applied pressure gradient. Okay. Therefore, the friction factor, okay, the shear stress should be only a function of the viscosity, the velocity, and the diameter. Okay. That means that tau w is equal to some constant times viscosity times velocity divided by the diameter, okay, which means that the friction factor is equal to this constant into mu u by d into 1 by half rho u square, which will be equal to 2 c into mu by rho u d, okay, which is equal to 2 c by Reynolds number. Okay. So, in the limit of very low Reynolds number, where you have only viscous stresses, you do not have inertial stresses, the stress has to depend only upon the viscosity, okay, and therefore, it has the friction factor has to go as 1 over the Reynolds number, and you know the friction factor versus Reynolds number plot, log f versus log Re, okay, and in the limit of very low Reynolds number, this friction factor is a constant divided by Re, and this constant is 16. Okay. At the Reynolds number of about 2100, there is a transition that takes place to a more turbulent velocity profile, and after that the friction factor will depend upon various things like the roughness of the wall and so on. Okay. So, the friction factor is the non-dimensional momentum flux in the flow through pipes and channels. Okay. And just from dimensional analysis, the friction factor in the case of flow through a tube for the heat transfer problem, we had scaled the heat flux divided by the thermal diffusivity. Okay. Here, rather than scaling it by the diffusion coefficient, it is traditional to scale it by the kinetic energy density, which is energy per unit volume. Okay. And that is the reason that in the limit of low Reynolds number, the friction factor goes as 16 over Reynolds number. Okay. Up to a Reynolds number of about 2100. Okay. After the Reynolds number of 2100, there is a transition to a turbulent flow, and the friction factor has a much more complicated profile. Okay. So, we have completed our dimensional analysis part of the problem. Okay. Basically, the takeaway from this section, you can do simple dimensional analysis, or you can do a more sophisticated dimensional analysis based upon what are the dominant forces in the system. Okay. In all cases, in heat, mass and momentum transfer, you are interested in predicting what is the average transport rate, or which depends upon, it's an extensive quantity, depends on the system size, or the average flux, which is the transport of energy, transport of that quantity per unit area per unit time. And we can define non-dimensional fluxes by using the diffusion coefficient to non-dimensionalize the flux. Okay. And that gives me the Nusselt number, the Sherwood number. Okay. And these have to be a function of other dimensionless groups. Those dimensionless groups have interpretations. They are mostly either the ratio of convection and diffusion, Reynolds number, Rayleigh number. They are the ratio of two different diffusivities. Okay, for example, the Schmidt number is the ratio of momentum diffusion and mass diffusion. The Prandtl number is the ratio of momentum diffusion and thermal diffusion. Okay. In the case of natural convection, you have dimensionless groups that are a ratio of, once again, convection and diffusion, except that convection is caused due to buoyancy forces. Okay. In the case of momentum transfer, flow through tubes and flow past objects, it is more traditional to define these dimensionless groups in terms of the drag coefficient or the friction coefficient. Both of these are momentum transport rates scaled by the kinetic energy per unit volume. Okay. And these, in the case of momentum transfer, these dimensionless transport rates are functions only of the Reynolds number, because there is only convection and diffusion. In the case of heat and mass transfer, there can be ratios of other both convection and diffusion of heat and mass, as well as inertia and viscosity, because the velocity profile that basically determines the rate of transport is determined for the fluid by the ratio of inertia and viscosity. Okay. And so, all of these dimensionless groups have this common form. Okay. Now, in the remaining course, okay, so I have told you what can be done so far with dimensional analysis. Okay. In the remaining course, we are going to try and give some motivation for why these kinds of things come up. Okay. So, for example, for the drag force in the flow around a sphere, for example, okay, I know that the drag force just from dimensional analysis has to got to be equal to mu r u times some constant. I do not know what that constant is. If I want to find out that constant, I have to solve for the velocity around the object. From the velocity solution around the object, I can get the stress on the surface, integrate the stress over the entire surface in order to get the total force. Okay. Similarly, for these flux problems, okay, for example, Nusselt number is equal to 2 plus 0.59 times this. Okay. I have to solve for the momentum transfer near the surface, and from that I have to find out what is the total flux. Okay. So, I need the entire temperature field around this object as well as the entire velocity field around this object. For the flow around objects, okay, why do these kinds of relations come about, okay, in the limit of high Rayleigh number for laminar flows? Okay. I have to solve, I am given, in the case of forced convection, I am given what is the velocity around the object, but I do not know what the temperature is. Temperature is transferred by convection along with the velocity, it is also diffusing across the object. I have to solve for those two independently in order to find out what the temperature field is. From that, the gradient of temperature at the surface times the conductivity will give me the flux. Okay. So, the remaining course will focus on these different forces, we actually try to solve for the entire problem, okay, around the object. Difficult to solve for the entire problem, but can we make approximations in regions where we expect either convection or diffusion to be dominant? Okay. If the Reynolds number is small, momentum diffusion is large compared to momentum convection. Viscosity is large compared to inertia. You can neglect inertia and solve for the problem by just balancing the viscous forces. Similarly, when the Rayleigh number is small, convection is small compared to diffusion. You can solve for the diffusion problem alone. Okay. Neglect convection and just solve for the diffusion problem. From that, find out what is the temperature profile everywhere. Okay. Opposite limit. Okay. Rayleigh number is large, convection is large compared to diffusion. Simplistically, one would expect that one can neglect diffusion and solve for convection alone. It is important to remember, however, that convection is only flowing material past an object. Okay. There is no convective transport to the object perpendicular to the surface. Ultimately, convective transport perpendicular to the surface has to happen, ultimately transport perpendicular to the surface, fluid velocity at the surface is 0. There is no transport perpendicular to the surface. Therefore, transport perpendicular to the surface ultimately has to happen due to diffusion. So, even if you have the ratio of convection and diffusion to be large, ultimately very near the surface diffusion has to become important if material is transported to the surface. Okay. So, in that limit we will see there will be a boundary layer very near the surface where convection and diffusion are the same, even though in the bulk of the flow convection is large compared to diffusion. Okay. How do we analyze these different problems? Okay. So, that will be the subject of this course. Next class I will tell you the basic framework of what we are going to do in order to analyze these problems, and then I will look at a more microscopic description of diffusion. Okay. How does diffusion arise from a molecular scale? How do I calculate the diffusion coefficients knowing what the molecular properties are? We will look at the class after next. So, next class I am going to tell you briefly, in a brief summary, how we solve these problems, and then we will go on to diffusion. Okay. So, with that we have completed the basic introduction to the course, and I will tell you something about the kind of description that we will use in the next class. Contrast this with the present description, where primarily we are dealing only with dimensionless numbers for the entire system. Okay. Average flux for the entire system, average temperature gradient for the entire system. Okay. In next class we will look at more fundamental quantities.